Quick note before we start. This narration is AI generated. The author's spoken English is, in his own words, worse than his model's calibration. The editing is code generated too. Everything else, the research, the results, and the mistakes, is entirely human. Okay, let's go. Large language models make things up confidently. But here's the strange part. There is growing evidence that the model, in some sense, knows. Deep inside its layers, a signal is there. I'm not sure about this one. It just never reaches the output. This video is about an architecture that builds a wire from that internal signal directly to the model's behavior, without changing a single weight of the base model. It's called meta-attention. The standard fix is to ask the model to reflect. Think step by step. Are you sure? Check your answer. This is text reflection. The model writes something, then rereads its own words. But think about what's happening here. The model's internal state, millions of activation values per layer, gets compressed into a few dozen tokens of text and then read back. Text is a lossy bottleneck. If the uncertainty signal didn't make it into the words, rereading those words won't recover it. The model is trying to diagnose itself through a keyhole. So what if we skip the text entirely? Here is the idea. When a transformer processes text, every layer produces activations, vectors that encode what the model is thinking at that depth. Instead of asking the model to describe its state in words, we tap those activations directly. A small trainable encoder compresses each layer's state into what we call a cognitive token, one summary vector per layer. Then, and this is the key move, we inject those tokens back into the model through cross-attention. Every layer can now attend to a compressed summary of what every layer was thinking. Attention over the model's own attention. Meta-attention. The base model stays completely frozen. We're not teaching it new facts. We're building a feedback wire that was never in the original architecture. At inference time, one query becomes two forward passes of the same model. Pass 1, read. The prompt goes through the frozen model, hooks capture the hidden state of the last token at every layer. That's the decision point, the state from which the model would predict the next token. The encoder turns those states into cognitive tokens and fills a buffer. Pass 2, write. The model generates its answer, but now, at every layer, cross-attention modules let it peek at the buffer. The model answers while seeing a summary of its own first impression. Let's open the box. Component 1. Activation hooks. Pure engineering. A forward hook on each layer grabs the hidden state of the last token. No parameters, no interference. Component 2. The cognitive encoder. Each layer gets its own tiny projector layer norm, a linear squeeze from 4096 dimensions down to 256, and a nonlinearity. A bottleneck this tight forces the projector to keep only the essential signal. Each projector also has a learnable gate, a dial that says how much this layer contributes. The model learns which of its own layers are worth listening to. Component 3. The meta-attention heads, one per layer. They work like classic attention with a twist. Queries come from the layer's current hidden state, but keys and values come from the cognitive tokens. So each position in the text can ask, given what I'm processing right now, which layer's summary is relevant? Everything runs in a compressed 256-dimensional space, half the cost of full-rank attention and empirically cleaner. And component 4, every injection passes through a gate, a single learnable scalar wrapped in a tan. The gate controls volume, not content. A layer that doesn't need introspection can simply close its valve. This near-silent start is also what makes training stable. The model begins almost identical to the unmodified base. Training is almost embarrassingly simple. Plain language modeling cross-entropy. No exotic objectives. For each question, we know whether the model got it right on its own. If it did, the training target is the correct answer. If it didn't, the target becomes either a correction or an honest refusal. I'm not confident enough to answer this. Here's the elegant part. The gradient flows backward through the frozen model, the weights don't change, but the computational graph passes the signal through, down into the encoder and the attention heads. The frozen base acts as a proxy loss function. The encoder isn't trained to predict correctness. It's trained to produce tokens that make the frozen model behave correctly. One rule turned out to be non-negotiable. The base model must stay frozen. Every attempt to unfreeze even a little, partial unfreezing LoRA adapters, 10 separate experiments, ended the same way. The model finds a shortcut. It optimizes the loss directly through its own weights, ignores the metachannel entirely, and the refusal behavior collapses. Capability isn't the issue, calibration is. The metachannel only learns when it's the only path to a better loss. So does it work? On MMLU with Llama 318B, when the model chooses to answer, it's right 89% of the time. But the headline number is refusal precision, 99.84%. Out of roughly 350 refusals, exactly one was a question the model could actually have answered. When this model says, "I don't know," it's right about that. The trade-off is real and worth being honest about. It refuses about 2/3 of the questions. It hasn't gotten smarter. It has switched modes, from answer everything, often wrong, to answer when confident, refuse when not. For a medical or legal assistant, that second mode is exactly what you want. Here's the result that suggests this isn't just dataset memorization. Take the checkpoint trained only on multiple-choice science questions and run it zero-shot on open-ended trivia. A completely different task format. Refusal precision 100%. Not a single unjustified refusal. And the map of which layers open their gates is identical across both datasets. Early layers stay shut. Late layers, especially layer 29, right where the model commits to an answer, listen the most. The encoder didn't learn the dataset's patterns. It learned the model's internal language of uncertainty, and that language is the same everywhere. One more finding I didn't expect. Train the same architecture on easy questions the base model mostly gets right, and the gates close to nearly zero. The model decides introspection isn't worth it. Train on genuinely hard questions, and the gates stabilize wide open. Task difficulty acts as a hyperparameter. The model regulates its own self-awareness based on whether it actually needs help, which is oddly relatable. Full disclosure, this is a solo side project, one person, evenings, about $30 of cloud compute. The numbers come from my own eval harness, so don't take them on faith. Code, weights, and every failed experiment are public, links below. If the model already knows when it's wrong, maybe the answer was never to make it think harder in words. Maybe it just needed a wire. Thanks for watching.